So today I'm going to talk about ICMP messages, and this is an acronym. You could eventually you'll memorize it. It's Internet Control and Messaging Protocol. Now there are in the life of the internet there are billions and billions of these little packets floating around, and they're just small little messages that get sent and received all the time. And I could they're one of the things that they're called is the garbage of the internet. And so this is I heard that many years ago, and it always stuck with me. That ping traffic is just it's zipping around the internet all over the place, and routers use it to communicate with other routers, devices communicate with other devices. We have network monitors that are set up that are designed to interpret and send out interpret the ICMP messages. Now, there are common messages and there are some that are not so common. One of the most common is we would call it a ping. It is an echo request, and then what you get back is an echo reply. But before we can do that, we have to have some other informational messages that we built into this protocol to give us some information. Basically, the idea is that if I were to send some information out over the network and I never received a response, I would have to begin to make some assumptions on what was going on. Because if I sent out the data and I didn't get an immediate uh, error in the physical or the data link layer, my network layer would need to begin to get some information. So if I send out a datagram and it goes out on the wire, I'm expecting a response. In TCP, my response is an acknowledgement. In UDP, I don't get a response. So I put some data out there, and by definition, uh, I don't, I'm not required, right, to receive a response. However, it's customary, right, to be able to um, respond to events that occur. And especially, we could use this for things like traffic management, for host monitoring, uh, all types of all types of reasons why I would want to have some type of informational protocol. And so that's why ICMP was created. It was designed to monitor hosts. So we have this idea of host reachability, and then I have some. This is the control process, right? Destination hosts unreachable, service unavailable, things like that. We see some of these types of things echoed in our application layer protocols. For instance, the HTTP protocol has many more uh, informational codes that are available in it, and we can use these. But in terms of network, the network layer, there aren't as many. There are a few, and so there's an RFC that actually governs this, and this particular RFC was dated in 1981. They've expanded it a little bit since then, but essentially, what happens is that we have a code or a type, and then there is a code. And then we have some information that we can yield from that. So this is just an example of I'm going through the RFC. And so in my ICMP packet, I have both a type field and a code. So my type of packet, destination unreachable, is type 3. And then I have some other information that I can code in here. So because of this, I can make these messages very, very small, and I can also make them very informational and very predictable. So that's something that is consistency, predictability, size, and an amount of information that I can get out of it is very important. And from an engineering standpoint, I want to be able to get as much information out of my network process as possible. So in this case, if I were to throw off a packet with type 3 and a code 1, my interpreting program is automatically going to know, oh, the host is unreachable. So I can return an error code that's consistent with that particular packet, or maybe this port unreachable, fragmentation needed. These are informational packages that I can immediately know what to do. And so, as an application designer at that point, I have some processes that I can put in place. So if I'm interpreting this packet, I don't have to check much, right? I just have to check the type, and then of course I have to do a check on the code, and I can automatically know how to branch my application and do something different. So here's another example. This is time exceeded. Every packet has a TTL, or time to live, and at some point when it hits the router, we know that we take the obviously take the Ethernet header, Ethernet frame header off, and we look at the actual datagram. And when we rewrite that header for the destination to go, and we forward the packet, we decrement the time to live field. We reduce it by 1. And so if that packet's already 1 and we reduce it, it is at that point a dead packet. And so the nice thing to do is to produce an ICMP packet that says time to live has been exceeded on this packet. Now notice that there are 2 codes that we can deliver with that. We can actually just send the code 0, hey, the time to live exceeded, or we could actually code in the 1, which is a fragment reassembly time exceeded. So essentially what happened there is I had a packet that was fragmented. I never received all of it, and so my timer expired in terms of holding that information. So I'm gonna create this informational product. Now the thing doesn't have to be very big, and notice that what I have when I send that back out is I put the header on it plus the 64 bits of the original datagram. And this is true for all of these. 64 bits of the datagram, the IP header plus the first 64 bits of the datagram data, and it's used by the host to match the message to the appropriate process. So I can actually, I'm gonna include my original packet, part of it anyway, and that way I can know which one it is. So all these types here are available. Now this one is a time exceeded type 11, which we already looked at that one. Destination unreachable type 3. Okay, So what can I get out of this packet that has a type field of 3? I can find out quite a bit of information about this unreachable destination. The network might be unreachable. That might be something that's delivered from a router that is somewhere in the middle. The host is unreachable. That could be something that's delivered by the destination router at the final hop. When it can't find the IP address that it's supposed to deliver this packet to. The protocol unreachable. Maybe there is a request to a particular protocol, and I don't have that running on that host. Okay, I don't have HTTP port 80 running on that. Boom. Icmp type 3 code 2. Okay. Port unreachable. This will be an example of the port's not open, right? Once it finally gets to its destination, the host says, "Yeah, I don't know. I'm gonna go ahead and I can't find that port. I'm not listening on that port. So I'm gonna generate this ICMP message. Not just routers send those, but hosts send these, and these really are gonna give me a lot of information. Now, again, like I said, there are billions and billions of these packets that are traveling on the network. This is an example of, I just typed in the network monitoring tools, and you can see, kind of like the images here, the dashboarding is really popular. I may have, thousands of hosts on my network, and the network could be geographically dispersed. I might have hosts in, a certain state or a certain location, certain networks of IP addresses. Um, because of because of WAN technologies like VPNs and whatnot, I can connect networks that are uh, geographically dispersed and bring them into a local subnet. But anyway, I'm going to be able to have uh, systems that are set up that just basically either send out ping traffic to all my hosts or receive ping traffic from hosts or devices. And this is I just did an image search, right? So I'm just kind of showing you the idea. This is kind of an example of what you might see in a dashboarding tool where I have lots of hosts that are out there, and I get some type of readout on whether that host is up or down. So every so often, I'm going to send out a batch of these echo requests, and then I'm going to get hopefully a batch of echo replies. And in this particular case, if that reply comes back, uh, it stays green. If I get another type of echo reply, or I get none, I might get a red. The yellow could be indicators of the fact that there could be some network delay, right? I may have a threshold set where I say, well, if my packet comes back in 5 milliseconds or less, I want to keep it green. If the transit time between the time I sent the packet and the time I receive it is more than 200 milliseconds, I'm going to go ahead and mark it yellow. And that gives me a visual representation of what could be happening on my network or with my devices. And so there's all kinds of different applications that are set up in dashboarding. You could take any type of solution to make that happen. There are lots of tools that are out there already. MRTG, the Dude, lots of different tools that are dashboarding tools, and everybody likes to make those because they're probably fun to make and do some different things with. But anyway, that's an example of using the ICMP protocol. Now, ICMP is governed by a couple RFCs. The one I was looking at before, 777, is not the latest. That's one that's updated. There are other RFCs. In this case, there is RFCs for ICMP version 6. The ICMP version 6 format is going to be a little bit different, mainly because the addressing has to be larger. Obviously, you go from a 32-bit IPv4 address to 128-bit IPv6 address, and things happen, right? You get a bigger packet. But I wanted to show you one historical issue that came back in a ICMP packet, and not a time exceeded, source quench. And the RFC is good. I'm going to link to this RFC in a Blackboard so you can actually read it and see what you might find some good information in there, especially the descriptions. There is an echo reply. Okay, yeah, here we go. Okay, so this is an echo or an echo reply, and notice that we don't reproduce the original datagram in that. When we send an echo message, it's going to have this type code 8. And then when the device sends a reply, it's going to have this type code 0. But notice that I could have some data in this packet. And it says that the data received in the echo message must be returned in the echo reply message. So I want you to imagine, okay, this situation where I have some host and I send it an echo request, and in the data field of the packet, I go ahead and fill out some information, and I try to make that as large as I can, right? So my host receives that packet, and it has to create a packet that contains the original payload and response. Now, it's possible that what could happen is that I may not have enough data buffer on my host to handle that receipt. And so when it gets received and it goes and tries to read all the data and then rewrite the packet, and in the echo reply, it ends up exceeding the buffer size. And so this is a very classic example of, and what happens is that the host either it fails to be able to respond to future requests, which knocks the host off the network, or some other unintentional consequences might occur, like the fact that any request that's received gets responded to. But this is a classic example of what we used to call the ping of death. So I send a very large ping message to my host. My host is bound by the specifications to create a response packet and include the original data. The only thing is the original data is too big and its buffer gets full and it is dead in the water to the network. So that was the classic ping of death, and that's since been resolved with buffer controls and whatnot. Uh, but that was a very historical aside on that. Is that that's something out there. So it's an example of you really have to watch what you put in the specification. It's very interesting that no one saw that originally and put some type of hard limit on the data that can be sent by that host. But anyway, this is the RFC for that. So I'll put that in the chat. I wanted to show you real quick what that ping looks like. And so I have a VM running here. Earlier this morning, I was in the process of doing some demonstrations here with the Wireshark, and I had a aptitude issue, and so I had to actually update my package manager in order to install a traceroute program. But we're gonna run some pings here, and you can see this. So I'm gonna go ahead and ping good old Google. Now I don't want to do a whole bunch of it. I'm just gonna do a couple packets, and just gonna go ahead and stop that. Okay. So what ended up happening is a couple things here that we can see. For one, I sent a my network created this Icmp echo request. We'll just take a quick look at it. We see some data in it. It's random data. We put the data in there because we want to be able to actually have the host process the packet. So this is it's just padded with data. Now, it's possible that I could have a host that utilizes Icmp and the data inside the packet to put some stuff in here. I can tell my ping command to pad the packet with certain types of data. We'll take a look at that as well. But I have done that, and immediately what has happened is I have received an echo reply. Now we're going to look real quickly at not at the data in the packet, but we're going to look at this type. So do you see this type message, type 8, code 0, right? So if we wanted to go and actually confirm that with our uh, RFC, notice they have type 8, and there's no code for that. Okay, and then here's the reply, type 0. And Wireshark, the dissector in Wireshark automatically decodes that, right? So he looks at that, the rules, and it tells me when I look at that type code, in this case 0 here, I can see that it's an echo reply. And so then here's my next packet. I send another one out. Ping. Really, when we look at that, what that is, there's not a lot of information there other than that host is up. But notice if I go and look at just a quick summary of my ping command, I can do a couple of other things. Contents of the padding byte. Tag the packets going out. stop after a certain number of packets. So let's go ahead and change the padding back. Okay. Notice that in my data frame here, I have placed in this pattern that was not there before, right? So that is that actually comes from my. If I see this other one, let's see. We'll look at the original one, the request here. Notice that it's just numbers. It's just random numbers. So when I put in my next request and I change that, I'm actually putting in some data right here. So I could put in something else. Let me go ahead and show you that again. Needs to be hex. Maybe we can do that. Let's see. Okay, so we'll just go ahead and do a ping, and I'm going to put my name in there. Okay, so here's my request. Notice that now I have placed my name in this packet. So do you think that I can't exfiltrate some information using ping packets? I certainly can. Now notice that what it did was it actually packed that packet with this data. It repeated it over and over and over. So that's pretty fun. But anyway, notice so the specification says that this data frame that is included with the packet has to be sent in the reply. So let's look at our reply and let's look at our data. Sure enough, there it is. So that's kind of fun. You can play with that and see it. The next thing is traceroute. We're going to show you this. So I take this idea of the fact that that I can do a ping and I can get a response, and the fact that when I have a request, now we can look here at this Internet Protocol header, and we can look at this time to live. See that 64? All right, so that's the default value. I can change that value, of course, with my ping command, but this is a default value. It means that every time I hit a router, I'm going to decrement that TTL counter. So knowing that every time that's going to happen, I can build a utility that does just the opposite. So, and we talked about traceroute before, but I want to show you how it works. And there we go. Okay. So now I got there pretty quickly. In this case, it actually never really made it. Let's see. Yeah. Oh, good. That's good. So, look. This is very interesting. We're going to just pick this apart. So, notice we have this ARP request going on here. Who has 10.0.2.2? Who is that? Right? So we have an ARP request going on. We're trying to figure out what's happening. Okay, and then this is my first traceroute message. I noticed my data in this packet, by the way, it's just padded with random ABCs. Notice I'm sending a UDP packet, right? And then I have a time to live of 1. So this is the time to live only 1. That's the Wireshark saw that and said, that's weird. Why is it only 1? That's strange. Okay, but so obviously it gets to the router, and I get this nice, wonderful control message back. Icmp, top 11, code 0, time to live exceeded in transit. Nice. Okay. So this is actually going to happen a couple times because the traceroute utility is designed to. This is actually, you see this 1, 2, 3. So I'm going to do this 3 times. Here's my next packet. Here's my time to live exceeded. There's my next one, time to live exceeded. And then I send out 3 more. Now, notice that the time to live value on that packet is 255. Right? The idea is that I'm going to maximize that one, and I want to be sure that I get that out to my however I have to route that, right? It's saying if you have to go to 255 hops in order to get that packet back to its sender, do it. Okay. So here's another packet. Internet protocol, time to live 1. Okay, now here's my response, and then here's my next packet. Now, you may be asking yourself, why does Wireshark color this red? The only reason why is because I told it to. It's well, not me, but it's the profile that's loaded in there. I could make it purple if I wanted to. Right? The red's just there for me to visually go, oh, there's an issue. Okay, so notice the next thing that happened when I decided to go ahead and send out another round is I incremented my time to live indicator to 2. So now what happens is I'm going to get to the next step in the process, the next router, if you will. And that router is going to give me a time to live exceeded in transit message. We can look at that down here. This is my original packet. Top 3, code 3, and then here is, see, this is my original packet information that I sent. It helps me identify which one I'm responding to. Notice that Wireshark automatically tells me which ones. So time to live 2, this is in my internet protocol header. Sorry, wrong packet. Time to live 2. And so what happened? Did I make it? I didn't make it. Alright, so then I'll try it again. Time to live 3. Time to live 4. It's trying. It's trying. Destination unreachable. Time to live 4. There's my response. Time to live 5. Right? I keep trying this. I really want to get there. I think if I keep sending out packets and I increase my TTL and my TCP header, time to live 6. If I keep doing it, maybe I'll make it, right? And then what happens? Unreachable, unreachable, unreachable. And eventually it gave up. Right? So that's my problem here, is that I gave up. More than likely I just didn't put any parameters on that. Mac TTL. Right, so I could send out some more. Let's do it. Dash in, let's do 15. Let's see, sometimes it helps to start over. Now what I should see is that every time I send out packets, I'm going to increment my counter. I made it to 6. It's very possible that this could be a issue of running into a VM, because I'm running a VM. I don't know. I'm gonna try doing that here. Let's see. I don't think I have that installed, so I'm gonna go ahead and put it in. There is a difference in the way the utility operates under Linux versus PowerShell or Windows. They operate completely differently. And okay, now notice that this particular utility automatically sets my hop count to 30. It's going to keep going until it hits the TTO hits 30, and then it's just going to stop. It's sending 60 byte packets, so it's putting some random data in there. And basically, I think what's happening is my packet's not getting, it's not receiving responses. So let's see, traceRT is my Windows utility. Now the interesting thing is here is this particular utility is going to report on the address of the host that sent the time to live exceeded message. So it's actually getting through in this case. More than likely what's happening is that my Windows subsystem for Linux is just not able to read those packets from the TCP layer. So the layer there that's interpreting the packets just is not being, the data is not being passed through to the application. And I'm not sure if that, I think that is an administrative issue. If possibly if I ran it as root, yeah, I don't think it's doing anything there. Oh well, but we can see that it works in under the Windows. It just runs a little bit differently here, but I can trace the path of that packet. It's the eventually after this router begins to stop forwarding it, I'll get this return message. That time to live exceeded at every hop until eventually it gets to a destination, Google DNS, and I can see the round trip time that process took. So there's just some information about Icmp. I hope you enjoyed this and that you learned quite a bit from the lecture, and also looking at how to pad these packets with some different data. Hopefully that was informative to you as well. And then we can learn a lot by analyzing packets. So again, these messages travel across the internet. There are just millions and millions and millions of them at any given moment, and they're very small, and so we can learn a lot, mainly because we know how to interpret them. Hope you enjoyed that. Thank you very much. Be sure and email me your questions so I can address them in future videos.